Okay, so we arrived to the result that E prime UB is this scalar product. I want to clarify this scalar product. Let's see. So you recall that I had, let's say, key x, y, to real part u, y, by, okay, ux squared, okay, dy dx. This will be equal to, well, ky minus x. Okay, this is a convolution. We can change this. Ux squared dx, and then outside u y conjugate by dy. So this what is telling us is that we can have a k convolution, let's say, to r e u b, okay, uh, ux squared to be equal to k convolution u squared u b. That is what we had. Okay, that's why I put 2 times this. We have the 1/4, and we could sum up and give only 1. Okay, so we finally obtained this. And what we want to see is that e of ut is equal to e prime ut ut. Okay, and so now this will be equal to, well, we can put this is square root u, and now ut plus k convolution u squared u ut. Okay, and we can make all this one u plus convolution k u squared u all ut. You recognize that this is what we had in the equation. Okay, so we can call this e prime of u ut. So we finally got that the derivative of ut is this scalar product e prime u ut. Okay, so we have e is in c1 h01.5 r. Okay, so we can compute in a well-defined way for t1 t2 in 0t. Okay, as follows. E of, recall the operator m, e m epsilon of ut2 minus e m epsilon ut1 to be the integral, okay, of t1 t2 of what we said it was d dt e. Okay, so this will be what it will be. It will be this e prime u ut e prime, but in this case we have me ut, so instead of ut we put m epsilon, let's put u comma ut, but then now we have m epsilon, and instead of ut let's use the notation u point. Okay, t, okay? Remember the t. Okay, so this will be equal to integral t1 t2 of real part. We will always be taking this real scale product of, well, we know what is this is, let's say a, we call a being the square root operator, and epsilon u plus, well, now recall f, the notation for the convolution part of m epsilon u. Okay, so we just made, just put this with m epsilon u. Okay, now we have that is this plus this. So, and now m epsilon u point, well, u point, we know what it is because of the definition of the Boson Stars equation. So this will be minus I m epsilon au plus fu. Okay. This minus I, that comes from the, if you recall, it was ut equal to a of u plus fu. Comes from here. Okay, so dt, okay, this will be equal to take the I away, and we ask for the imaginary part. Okay, and now we will make this with this, this with this, this with this, and this with this. Okay, that will be a m epsilon u comma m epsilon u. Okay, this one with this one, we get rid of the I, and we ask for imaginary part. Okay, so m a m epsilon u m epsilon, this is au, and okay, au comma plus f m epsilon u comma m epsilon au plus a m epsilon u comma m epsilon fu, that is this one with this one here with an epsilon, and finally the last one is f m epsilon u m epsilon f of u. Okay, that is the last one, dd. Okay, recall that this minus goes out as conjugate, so we'll stay all positive. Okay, so now let's make some room, and let's call, what is this all inside, let's call it f epsilon t. Okay, what is inside. Notice that in this term, if epsilon would be equal to 0, then we'll have au comma au, and then we will have two functions in h1, h minus 1/2, that is what we don't have defined. So now with the help of m epsilon with epsilon greater than 0, now we can do this pairing of these two functions. Okay, so now we'll use the fact that m epsilon a is equal to a m epsilon. Okay, this holds because well, we will have, for example, that a m epsilon u and m epsilon au are both in h1/2. Remember that if we apply first a, it will be in h minus 1/2, but this will give regularity to h1/2, and here we'll have s plus 1, and this will take it down again. Okay, so both will be image 1.5. Okay, so knowing that, we can go to we can see that the image part of imaginary part of a m epsilon u m epsilon au is equal to, well, a m epsilon u, comma, now a m epsilon u. We know this is real, so the imaginary part will be 0. That means that the first part of the integral, this, is equal to 0. Okay. Okay, so with this, now we will have that we have this is f epsilon, and so now we will say that this is equal to the imaginary part of, well, now let's say a1.5, we will take 1.5 from this side and take it to the other side, f m epsilon u, okay, a1.5 m epsilon u, okay. And then again we will do the same for this term, a1.5 m epsilon u, okay, comma a1.5 m epsilon f u, okay, plus another term f m epsilon u, well, this will stay the same, m epsilon f u, okay. Okay, so since m epsilon u converges to u strongly, in h1.5, as epsilon goes to 0, then we will have that the limit when epsilon goes to 0 of f et will be, well, the image part of a1.5 f a1.5 u plus a1.5 u a1.5 f plus here f. So you can see in this last term we have the same, and here if we add this one plus this one and this one plus this one, we will have also the same. So we can say that this conjugate is the same as this, so plus this is the imaginary number of a real number, so this is 0. Okay, so to interchange the epsilon limit with the t integration, we appeal to the dominated conversion theorem, that is, we seek for a uniform bound on f epsilon, and we can use Cauchy-Schwarz inequality. This is what we want to bound, so let's put all what we have between the absolute value. Okay, so we put all in the absolute values, and now we can bound with Cauchy-Schwarz theorem. Okay, so we will have this bound. Okay, this is for the first, then we will have the same for the other ones. Okay. Okay, so we have this bound because of Cauchy-Schwarz, and now we're going to use the first lemma. Okay, so now we can bound f of u by this bound from lemma 1. We can uh, take this bounds f of u. This is just using the Lipschitz, and this is from the release potential, and we will use that. We will obtain u force h1.5 force u 6 h1.5. In the next video we will see the final conclusion to conclude that the energy is conserved. Okay.